Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for joining this session. I'm super happy to be here in PyData Global. Today, I'll be giving you a talk about sliding into causal inference with Python. We have a very packed agenda today. We'll start with an introduction. I'll tell you what I mean when I use that term sliding, and we will cover the gold standard for causal inference. And then we will spend the majority of the talk discussing what happens when you can't use that gold standard. So we will talk about common reasons and we will talk about common solutions. And then finally, we'll do a quick recap about what we've seen and where you can go next in your journey into causal inference. Before we dive in, just a couple of words about myself. I'm a senior data scientist at Spotify. For obvious reasons, I'm not going to discuss anything that I'm working on at Spotify. I'm based in the UK. You can find me on Twitter, LinkedIn, GitHub at Alon Nir. And I will admit that still, I quite often read causal inference as casual inference. And if you didn't know, casual inference is this really chill and laid back variety of statistics. Because the topic is so huge, my approach today would be oversimplification and exuberant hand waving. I care about giving you kind of the intuition about, how certain things work and why we would need to use that instead of one method instead of the other. And then if you want to dive deeper, the slides and the code for this talk are already on GitHub, so you can check it out at your own leisure. There's a lot more detail in the appendix for this talk. And then you can also see the code and follow line by line. It's really kind of simplistic and well commented, I think. So you should be able to kind of catch up on the nitty-gritty at your own leisure. So let's jump into it. When I was a wee little kid in the 90s, there was this show I really, really liked. It was called Sliders. And Slider was about this group of friends that they hop between parallel worlds. That guy in the yellow-orange jacket, his name is Quinn Mallory, super sharp guy. He invented a sliding device that opens a portal for them to hop between parallel universes. If you didn't understand already, I'm a huge nerd. And then every episode of the show started by with that guy, Quinn Mallory, saying, what if you found a portal to a parallel universe? What if you could slide into 1,000 different worlds where it's the same year and you're the same person, but everything else is different? So basically, that was a method to explore alternative histories. They would slide into similar worlds to our Earth, but one thing changed in history that kind of changed where they are now in the 90s. So, for example, what would a world without penicillin would look like? What would a world where the atomic bomb was never completed look like? And so on and so forth. And I found that idea of kind of sliding between parallel universes and exploring alternative history is really, really cool. So today, you've probably already been using simulations in academia and or in industry. And the question I have for you today is, well, can we use Python, of course, to build a sliding device like Quinn Mallory? Before we answer that question, we need to start from the basics. And so for the basics, we have this one example that we'll use throughout the talk. And that example has to do with my girlfriend, Emma. This is, of course, an artist's depiction of Emma. In reality, she is much more lovely, and most of the time she's three-dimensional, which makes things easier. And in addition to being a brilliant woman and for putting up with me, she also likes to knit and to crochet. And in fact, she is so passionate about it that she actually, not really, started selling wool online. And she called her shop, not really, Amazon. Now, Emma, living with a data scientist, she decided that, let's use data science to expand the business, make the customers happier, and so on and so forth. So let's get started with a randomized controlled trial, or an A/B test that you've probably heard of before. Basically, we have two groups we want to compare. So let's assume that every month, Emma sends her customer base a newsletter. And that newsletter always ends with a big blue button that says, buy it now or check it out now. Like there's a call to action, big blue button. And now what Emma wants to know, what would happen if everything was the same content of the email, but the color of that button would be orange instead of blue? Would that increase sales, for example? So what we would do in an A/B test, a randomized control trial, maybe you've heard of it as a multivariate test, which is more than just one treatment and compared to one control. What we do, we randomly split the customer base, 50% get the control, the same experience as always, 50% get the treatment. You see how each group performed. And the group where, that bought more wool is declared as the winner, assuming, statistical significance and all that good stuff. And that's how the bare bones of randomized controlled trials work. So basically, what we should always have in mind is that we have two groups, we have control, we have treatment. We want to know which one is performing better. Now, this was really kind of speeding through what a randomized control trial is. I strongly recommend you check out Jack van der Plas's talk from 5 years ago, but it's brilliant, one of my all-time favorites. He gets into more detail now how to compare two groups and see that the effect is real. And what we've seen just now, randomized controlled trials, they are known as the gold standard in causal inference. And the reason they're the gold standard is that because the magic of randomization works on observed and unobserved covariates. So an example for an observed covariate could be the city of residence, iPhone versus Android, and so on and so forth, all sorts of factors that might affect your decision to get more or less wool. And an unobserved covariate could be, for example, color blindness. So obviously, if you change the color of the button, people with color blindness might react differently than people who can see colors. And so if you had one group that was had a greater proportion of people with color blindness, that would be a factor that comes into play when comparing the two groups. And so randomization magically makes sure that the proportion of colorblind people would be roughly the same between the two groups. And here's a tidbit of information for you. Males are 16 times more likely to be colorblind than females. So imagine that, for some reason you would have one of the groups in the experiment had a greater proportion of men in it than the other group, then colorblindness would come into effect and you wouldn't even know because that's an unobserved confounder. So that's why we use randomization. Randomization guarantees that all of those factors, and especially the unobserved ones, are balanced between the groups. And that's amazing. That's the gold standard. That's what you should always strive to. So that's all nice and dandy, but what happens when you can't experiment? So there are all sorts of reasons why you wouldn't be able to use a randomized controlled trial. One of them is network effects. So random effects basically means that the group, the subjects or the units of measurement in one group affect the results of the other group. For example, if we are thinking about Emma's emails again, let's assume that the variant, the orange button, was so successful that whenever someone saw that email, they would immediately rush to the website and bought a lot of wool. And if they buy so much wool that they completely clear out the stock, when people who get the blue button want to kind of follow the button along and buy some wool, they don't have any. Not because they don't want to buy, just because there's none left in stock. And so the behavior of people in the orange group affected the outcome of the blue group and artificially decreased it. So that's an example for network effects, and there are many others. Other reasons have to do with immoral or legal perspective. For example, if you want to study the effect of drugs on kids, then you probably shouldn't give kids drugs to see what happens. And there are other practical perspectives like budget or user experience and so on and so forth. So what can we do? I want you to keep in mind that what we strive to, what we want to do is to use the gold standard. We want to have a group of control people and a group of treatment people and compare them. And you would see in this little graphic that the groups are heterogeneous, right? You don't see they are roughly looking the same. You don't see people with, more people wearing red in one group of the other and so on and so forth. So with that in mind, what we are going to look at is two examples. One of them will see what do we do when the allocation to control and treatment is not random, when it's biased, when it's skewed, and how do we fix that to be more similar to what we want it to look like, the randomized controlled trial. And then we'll start with that, and then we'll turn our attention to cases where you don't have a control group because everyone gets the treatment. But that's to come in a few slides. So back to Amazon. Let's imagine that every order on Amazon contains exactly one ball of wool. Delivery fee is £2 flat per order, and things are at a steady state. So nothing changes. If you bought 5 balls of wool last month, you'll buy 5 this month and 5 the next month and 5 the month after that, and so on and so forth. Now, Emma introduces a new service called Amazon Sublime. Again, not real. And Amazon Sublime is a subscription service that offers you unlimited free delivery on every order if you pay an £11 a month subscription fee. So how does that affect the business? So let's do what we always do. We have control, we have treatment, we'll compare the two. So the treated here are Sublime subscribers. We see that they order 13 times a month. We look at people that don't have Sublime. They order 4.7 times a month on average. We see the difference is almost 200%. So Sublime is a huge success. Or maybe it's not. So let's kind of have a closer look. Let's look at the distribution of orders before Sublime was introduced. And very conveniently, you can see that we have exactly 10,000 customers, and they are uniformly distributed between 1 and 10 orders a month. So you have 1,000 people that order once a month, 1,000 people who order twice a month, and so on and so forth. And they are very neatly, uniformly distributed. And now let's see what it looks like after the introduction of Sublime. So the horizontal axis is again the number of monthly orders before Sublime was introduced, and the vertical axis is the number of monthly orders after it was introduced. So very easily you can see that only people who previously, again, remember to look at the horizontal line, ordered 6 or more times, they are the only people who got Sublime, which makes sense. If you ordered 6 or more times a month at £2 per delivery, then you would pay £12 or more a month on just delivery. So getting an £11 a month free delivery subscription program makes sense. And for the same reason, people who order 5 or less times a month wouldn't get the subscription because they are already spending less than £11 for deliveries. And if we kind of go back and look at those highly engaged users of 6 to 10 orders a month, we can see that 50% of them got Sublime and 50 didn't change their behavior. They didn't get Sublime. So big bullets are representing 1,000 people. Smaller ones are 500. Blue is kind of the before, red or without Sublime, and red is with Sublime. So let's take our rulers out and see, well, those lines seem fairly parallel. And you know what? Actually, the difference is 5 orders. So how did we get 8.3? Well, the reason we got 8.3 is that we made an unfair comparison. Highly engaged users self-selected themselves to become Sublime members. It wasn't a randomized controlled trial. People who had more orders a month prior to Sublime are the only ones that would even consider getting it. So we didn't have what we wanted to have, similar groups of control and trial. And when we compared people who got Sublime to all the people who didn't get Sublime, we made an unfair comparison, which artificially diminished or decreased the number for the untreated. What we should have done is to compare those two groups, the two groups that were even eligible, would even consider Sublime. So this is what we needed to do. Those two oval shapes, we needed to compare people with high engagement prior to Sublime and high engagement post-Sublime and see what they behave like. And the way we do that is with a technique called propensity score matching. Propensity score matching is fairly simple, at least theoretically. There are 4 steps. First of all, you learn a model that predicts the propensity a user or any unit of measurement in your experiment would get the treatment. Then you match every user that was treated to a user that wasn't treated that has a similar propensity score. Then you compare, kind of calculate the delta between the two. And when you do that for every user, then you can find the average effect size for everyone. And we have code, which is again on GitHub, so we don't really need to kind of follow along. I basically have the same parameters as that we saw in the slides before. We have 5,000 people with low engagement, 5,000 with high engagement. The probability of getting Sublime, if you're highly engaged, is 1/2. And the uplift is exactly 5 orders flat. And then kind of stating those facts, then we can start building our kind of simulated data. And we can see that if we do some quick group buys, we can see that if you order between 1 and 5, the percent that converted is absolutely 0, exactly 0. And if you ordered 6 or more times, it's roughly 50%. It's not exactly 50% here because we use simulated data. And then the meaty part is kind of just learning a logistic model to predict the propensity they would get the treatment. So your regular vanilla sklearn logistic regression. And then if we plot stuff, we see that the model picked up that people who have higher frequency are more likely to get Sublime. So that shape is not ideal. What we would expect it to look like is this, the blue, teal, green bars that show that, it's 50% flat after 6 orders and not gradually going up. But that actually is good enough for our example. And I would challenge you to think of why. So we do that, and then we do the matching, and you'll follow along at home. And believe it or not, we get exactly 5 orders difference. And so everybody's happy. And I know this was hand wavy, so I would encourage you to go to the repo and check it out yourselves and be convinced, because the code is fairly straightforward. So just to recap, we saw that we have 2 groups, treated and untreated, but they weren't randomly assigned because there was self-selection. People self-selected themselves to get the treatment, which caused some inflation for the effect size. And we used propensity score matching to fix that, to emulate a random assignment, which is exactly what we wanted. Again, think about the 2 groups, control and treatment, similar groups. So we could compare them. And this was a very simple example of propensity score matching because we only had 1 covariate, the number of orders prior to the introduction of Sublime. But in reality, you would have many covariates. And if you think about the curse of dimensionality, the more covariates you add, then propensity score matching is a really, really useful technique because it reduces all of those dimensions to 1 number to match on. And that's the beauty of the methodology. So I hope that was clear. We just saw what you do when the allocation to control and treatment is not random. Now let's talk about what happens when You don't have a control group. You only have a treatment group. What do you do then? So again, we go to Amazon and let's pretend that all of that previous section didn't happen. Let's throw away all of the assumptions that we introduced earlier. There is no Sublime, nothing. And we kind of look more deeply into Emma's business, and she actually has 5 product lines, 5 different types of wool: green, blue, magenta, and so on. And we assume that each of those product lines have their own distinct group of customers. So there are people who buy only green wool, there are other people that would only buy blue wool, and so on and so on. So those groups of people are independent of each other. If I buy green wool, I only buy green wool. I don't buy any of the other colors. And the same applies for the other color wools. And they are completely, again, independent. The behavior of one group of customers of one color does not affect in any way the behavior of other colors. All right, I hope that makes sense. And if we look at the kind of the purchasing frequency, we can see that green wool customers place an average of 5 orders a month, blue 3, and so on and so forth. Now, here's the interesting part. Let's say that Emma decided to offer free delivery for everyone buying green wool. And again, only people who buy green wool would be affected. Other groups would not be. They're completely independent. They're completely oblivious. They're just doing their own thing. So what do we do? How would free delivery affect the number of orders of green wool that people make a month if we don't have a control group? Everyone gets free delivery. All right. So here's what we want to do. We want to have a group of control, a group of treatments. They would roughly look the same, and we want to compare them. But unfortunately, we just don't have that control group. What can we do? What we would want to do in an ideal world is to say, well, I have this customer. Here are the number of orders they placed with the free delivery promotion. Here's the number of orders they would have placed without the free delivery. We calculate the difference, and we kind of can estimate the average treatment effect or the effect size. So that would be in an ideal world, but unfortunately, in reality, we only observe one outcome. We only know how many orders each customer from the green group actually placed. We don't know how much they would have placed if they didn't have free delivery. Again, remember, we threw away all of the assumptions from the previous example, so we don't assume a steady state for the green customers anymore, for example. And this problem is known as the fundamental problem of causal inference, because we can only observe one outcome per person. We don't know what would have been the outcome had the person been under different circumstances. That's a biggie. So what can we do? We have all sorts of techniques to handle that. We have pre and post analysis. We have difference and difference. Both of these are covered in the appendix of this talk. They're very straightforward, so I don't bother kind of going over them now, but I do encourage you to check them out on GitHub. And what we will talk about is this technique called synthetic controls, which is our version of a sliding device, which is pretty cool. So what if we could build our own sliding device? It would show us a parallel world where all of those people who got the treatment didn't get it. All right. And what synthetic control does, it basically creates a counterfactual reality, what would have happened. And even if you don't have one good control group, what it does, it weights other time series, other potential controls that, even though not one of them is a very good control group by itself, it assigns weights to learn how would a counterfactual group would have behaved, and uses that to predict or to find the change in behavior. So this was kind of high level, so hopefully you'll understand better in a sec. So if I were to throw you back into your nursery days or kindergarten days, you would remember that if you wanted to create green color and you didn't have any, then you would just mix 50% blue and 50% yellow and you would get green, right? That's elementary nursery skills. And we need 0 magenta, 0 red. We would still, if we just take 50% of blue, 50% of yellow, we would get green, which is great. And the numbers kind of are working out. These are the numbers I showed you previously, and very conveniently, if you take 50% of 3 and 50% of 7, you would get 5. So things kind of make sense. In code, again, not going to bother going through all of this. We again kind of create the same starting conditions with a lot of randomness and simulated data. We do some descriptive statistics to see that actually things are the way we want them to. Things behave the way that we wanted them to behave. So green has an average of 5 orders, blue with 7-ish, and yellow 3. And then we are good to keep going. And the way we'll implement synthetic controls is with this very nice and handy library from the good people at Google called Causal Impact. And what Causal Impact does is uses black magic and Bayesian structural time series, which is completely well beyond the scope of this talk. And what they do is they kind of learn, they use time series of different control groups, they weight them to create a counterfactual, and this is what some of the outputs look like. So what are we seeing here? So we have a dashed line that shows the time of treatment, and we have a solid black line, which is the green order. So before the treatment, they are around 5. After the treatment, they go up to 7, but we'll get to that in a sec. The dashed lines with the purple bands are the counterfactual. So basically a mix of other colors that we can see that in the period before the treatment, they are fairly similar to what green actually looks like. And then we have the treatment, green goes up to 7, and the counterfactual, again, kind of the dashed line with the purple bands, stays the same because I didn't see the treatment. So we are using the same weights that would land in the period before the treatment and apply them to those groups, the yellow and blue ones, after the treatment too. And that allows us to find the difference. Hope that makes sense. This was a super simple example, how to construct a counterfactual. This was so simple that, in fact, it was wrong. And I challenge you to find why it's wrong. There is more information on the GitHub repo. When you get it, you get it. And I'm more than happy to chat further offline. So I hope you enjoyed this talk so far. Let's just do a quick recap before we break. We started by seeing the randomized controlled trials, which is the gold standard. We talked about what happens when we don't have a truly random allocation to control and variant. And then we discussed what happens when you actually don't even have a control group. And next up, you can kind of, if you want to explore or dive deeper into the world of causal inference, you can think about breadth and depth. So breadth, there are so many topics we didn't cover, like diff and diff, DAGs, instrumental variables, fixed effect regressions, and so on and so on. There's a lot to learn. And you can also kind of dive deeper into one specific topic like PSM. So with PSMs, we didn't discuss how do we know that the groups are balanced after we do the matching? How do we match? What function? What algorithm do we use for matching? Should we match with or without replacement, and so on and so on? There's all sorts of considerations, and there's a lot more to talk about when it comes to PCMs, for example, or any of the others. So just to leave you off, we discussed the fundamental problem of causal inference. I would like you to remember that even though we have, fancy math, shiny tools, we will never know if the number we came up with is actually true, because we will never observe that counterfactual Earth. So just keep that in mind. Here are a few links if you want to learn more. And I would like to thank you very much for joining. I really hope that you enjoyed this talk. Thank you very much. And I hope to keep the conversation going offline. Thank you.